Nowadays, for privacy reasons, we often need to hide certain details in photos, like faces or car plates. This is usually done using a particular filter, the so-called blurring effect. But how does blur actually work? Did you know that behind this operation there are matrices? Let's have a look together. Let us consider, for simplicity, this grayscale picture of a car plate. Where is the matrix? Once again, for simplicity, let's focus on a small portion and downscale it. This grayscale image is composed of 144 tiny squares called pixels, organized in a 12 by 12 grid. To each pixel of the image, we associate a number where 0 is black, 255 is white, and in between we have different shades of gray. At this point, the image can be represented as a matrix. Each entry is the grayscale value of the corresponding pixel, and in particular, each pixel can be uniquely identified by its row and column position. For instance, this pixel is in the 6th row and 9th column. To understand how to blur an image, it is important to highlight that changing the values in the matrix affects the image, and that the easiest way of blurring an image is to average out the values of neighboring pixels, for instance, using a simple arithmetic average. So for a given pixel, we replace its value with the average of these 9 values. And in this case, we obtain 90, which is a middle gray. This operation will then be repeated for each pixel, or more precisely, for each internal pixel of the original image. So how can we automate it? It is convenient to organize the weights used in the average in a 3 by 3 matrix. This matrix is called filter or kernel, or to be more precise, is the kernel rotated by 180 degrees. If we position this kernel over the image centered on pixel I and j, we can perform the average by doing element-wise multiplication of the two matrices and summing results up. At this point, we slide this kernel over the internal pixel of the original image, that is, all the pixels that have 8 neighbors. In this way, we build a blurred image which will be smaller than the original one. This process is called discrete convolution between the matrix A representing the image and the kernel K, which is a 3 by 3 matrix. The algorithm to compute each filter pixel looks like this. We need the image A, the kernel K, and the indices of the pixel I and j. We store the sum in a variable v initially set to 0, and we loop over the rows and the columns of the kernel to assemble the element-wise multiplication of the kernel and the portion of the image around the pixel ij. And as we go, we sum these products up in the variable v. It is worth focusing on the indices here. So the idea is to go around the pixel ij. This means that in the portion of the matrix A, the top left corner has position I-1, j-1, which correspond to m equal to 0, n equal to 0 in the kernel. Increasing m, we move down. Increasing n, we move right in both matrices. And keep in mind that this algorithm has to be performed for each internal pixel of the original image, so we need a computer code to do it automatically, and in the next videos we will learn how to write it.